next up, we have got Steganography, sorry if I pronounced that wrong, from Chevron Technology. Passionate about innovation and collaboration, comes from an electronic engineering background with 25 years experience in FPGA technology and semiconductor RTL design, delivering cutting-edge solutions to challenging problems.
Thank you. And thanks to Ian for the presentation. There just was a lot of points that we find very interesting in Cambridge Chevron Technology. So my name is Stein Gustafsson. I work with Chevron Technology. We worked with FPGAs for many years, developing solutions for aerospace, defense, and cybersecurity. Today I'll be talking about designing reusable, portable, and secure IP for FPGAs.
Thank you so much. So my sincere apologies for arriving late, but my computer crashed and I wasn't able to do anything. So my name is Pedro Machado, and I'm today here presenting about the work that I've been doing and the implementation that we have been doing in FPGAs. So the work is about bio-inspired CODECs, and where we use steganography, which is a technique that allows us to embed information into images. So let's look into the why and how. Okay, so my hypothesis is, can we transmit sound embedded in the image? This is especially important if you think about the context where you have applications running underwater and you would like to transmit sound, but nevertheless, if it's underwater, you have a limit amount of information that you can transmit. So you have to think very careful about which information is required. So if you are doing, for example, classification and you require the image, then you can start thinking about, okay, can I include some more information into the image because I really need to transmit my image back to the surface. So the question is, can we encode, for example, the sound into the image? And the other question is, one of the technologies that I'm going to cover today are called spiking neural networks. And spiking neural networks is considered the third generations of neural networks. So the question is, these tools enable us to have the same type of behaviors that we can see, for example, in human brains and animals as well. And one thing that I'm going to show you is that they are very hard to read. So how can we leverage from that to embed the sound into the image? So let's step back a little bit and think about what spiking neural networks are. So spiking neural networks are networks that that use neurons like we find in nature. And here I'd like to show you the action potential of the neuron. So if you look into a biological neuron, they will have a curve more or less like this one. While if you use classical neural networks, the ones we are using at the moment, you probably get a sigmoid or a hyperbolic tangent. So the principle, the way they work are very straightforward. So when they reach a specific threshold, let's say here, they will generate these bars, vertical bars that we call spikes, okay? So every time that voltage reaches that threshold, it generates a spike and then goes down and starts the process all over again. And if you think about FPGAs, this type of events, they are very easy to implement. So a couple of concepts so that we can understand what we are talking about is, this is the event-driven processing. So unlike traditional artificial neural networks that process all data simultaneously, these will generate what we call spike trains. So you have a specific size, a vector, think about a vector, and then you have events, okay? So if you think about one-hot representation, this could be easily implemented using one-hot representation, okay? There's another concept that is really important called the spike timing dependent plasticity. So a very simple way of describing STDP is just think about two neurons and they have synapses, right? And the time that it takes to propagate the spike across one neuron for the other neuron, that time will have an impact on the overall computation. So we say that STDP is unsupervised because the principle is if the pre-neuron spikes, then the post-neuron will, and if the post-neuron spikes, then there is a correlation between the post-neuron and the pre-neuron. And what happens is when they spike, then the weight of that synapse is going to increase by a specific amount. And at the readout layer or the third layer, the classification layer, the third one, we can use techniques like remote supervised method, which is you force the neuron to spike. You use a teaching neuron, an extra neuron that will connect to that neuron, and every time that you want to make the neuron sensitive to those patterns, you force them to spike. And as you can imagine, this is a very efficient way of representing information, and these help us to, in our case, to do bio-inspired compression. And I'm going to explain how. So the step that we normally do is we don't go straight to the FPGA. We need to step back a little bit and be able to do the simulation. And in this case, we use Nest Simulator that allows us to write the code in Python. And then in the next transition, what we do is we then implement the model into the FPGA. And for evaluation of the performance, we are going to use spike metrics. So spiking neural networks do not work in the same metrics that you use for classical neural networks because it's all about when the spike happens. So for example, you could have the same pattern, but is affected by a specific threshold because of this propagation delay. So we cannot use the same types of metrics. And in this experiment, what we did was to use the link integrated and fire neurons, which is one of the simplest neurons, okay? So what is the process? So we need, the first thing is to encode both the image and the sound, okay? And we know that an image has 3 channels, red, green, and blue. And we have n rows by m columns depending on the resolution. So we need the number of neurons that we're going to use in this experiment is n rows times the m columns times the 3 channels. So red, green, and blue. We also have the audio encoding. So we will require 6 neurons, and I'm going to explain why, times the number of the sample, times the number of samples, times the number of channels. So we have left and right. So we know that in the case of sound, a sample will have any value between minus 99,999 and up to 99,999. So we use one neuron to look at the units, another neuron to look at the tens, another neuron to the hundreds, thousands, 10,000, and then we need an extra one. Because this is a codec, so we have a one-to-one correlation, so we need 260 patterns to encode the image, because we know that a pixel can have any value between 0 and 255, and we need an overall of 10 different patterns to code any sample. So for example, the units goes from 0 to 9, the tens 0 to 9, and then the last neuron just needs 2 patterns, which is positive or negative depending on the signal. So we need then to think about the decoding spiking neural network. So we need the same number of neurons, because think about as analog to digital and a digital to analog converters. So once you encode the information and you now have the information using spikes, and I'm going to show you some examples on how they look like, Now if you want to convert back, you need to have to apply the inverse transform. Okay, so you need the same number of neurons to recover back the information. So as I pointed out, for the pixel values, because they are between 0 and 255, we need a total of 256 patterns. And as you can see here, this on the right-hand side is called the raster plot. What you'll notice is that you have completely different patterns. So these vertical bars that I've shown you before in the previous in one of the previous slides, what we are looking for is different patterns. So for example, we can see that the first neuron, when in the line 0, we have a spike in between 60 and 80, probably 75, 70 something. And then if you look into the other one on the top, you'll see that you have a spike closer to the 60. So this is what I'm looking for. We want a pattern that is unique for a codec. And I'm highlighting the codec because later I'm going to explain other possibilities that we can use this technique to do encryption, okay? And for representing our samples, we can see here the 10 unique patterns. So here is a little bit more relaxed because we just need 10 patterns that allow us to recover the information back. One aspect that I want to highlight is if you think about an image, and let me go to the next one. Okay, I'll be there. Before I go to the next image, I just want to quickly explain what steganography is. So we have, our goal is we have our raw image and now we have our sound, and we want somehow to hide the information into the image. We can call it hide, or we can say that we are just storing that information. So the technique that we use was the following. So think about the black color, right? If you do an exercise and if you test to check the difference using your eye between a 0 or a 1 in a pixel, you'll notice that you still have the same black, okay? So, and the same happened with the 2, and we did that up to the number 9. So what we did is any value between 0 and 9, we make it a 10. So, and by pushing the 0 to 9 into a 10, we are finding places in the image where we can hide information. The principle is the following. When we are reconstructing, we are just looking for pixels from the top to the bottom, from left to right. We are looking for pixels that have a value that is not a 10, okay? And therefore, what we do then, we use that space to be able to hide our samples or to store our samples if you prefer. So let's look at this example. The first thing that we have done was to try to do the conversion, to encode, and then to decode using the networks that we discussed before. So you can see here on the top, you have the original image, and then you have the reconstructed image. On the bottom, you see the raster plot. So the equivalent to that image where we see a leg and a shoe is that raster plot that you can see here on the bottom. And here I want to also to demonstrate that it's a very safe way of storing information. If you try to run a cryptanalysis algorithm, and by the way, this is just encoding on that pattern, it's very unlikely that you will all be able to recover the image like we did. The black image that we see on the right-hand side on the top is the absolute difference between the reconstructed image and the original image. So what we do is we subtract pixel by pixel, and if there is a difference on the value, that means that some of the information has been corrupted, and we'll see a white pixel here on the absolute difference. As you can see here, the output is a black image, and I actually checked to see if there was any pixel whose value was different from 0. We can also see a typical raster plot of the sound. So we encoded the sound that was associated to that video, and that was the result. As you can see here, once again, you'll notice that this would be very unlikely to be able to reconstruct the sound, even if somebody is attempting to hack into the system. And again, just to highlight, I'm still talking about codecs. I'm not even talking about cryptography at the moment. So let's look into the steganography and look into the errors. So we can see here on the left-hand side the original image, and then we have the mapped image. And to help you to understand where the difference here, where the difference are, look at this binary difference between the two images, and that's where the information of the sound is going to be stored. And even if you zoom in with your naked eye, it's very unlikely that you find any difference between the blocks. Okay, so these are the pixels that we are going to use to store our sound. So once we did the experiment, we started to do the implementation. But the question here is, what is the best way to implement this on an FPGAs? Are we going to use Verilog? Are we going to use VHDL? Well, we are doing research, right? So we need to make sure that what we do allow us to publish as soon as possible. So we decided to go with OpenCL because OpenCL is very similar to CUDA and allows to increase the compatibility between FPGAs. The only situations that you may come across, and I'm going to look into how which parts we can accelerate and parallelize and leverage in terms of parallelization. But one of the situations that you may have is if your device is too small, you may come to the conclusion that the acceleration may not be the one you were expecting because you simply do not have enough resources. So you have to make some decisions about pipelining. So the way OpenCL works is as follows. So you have the code that goes on the host, and then you have the kernel that runs on the FPGA device. And then what you have to do is every time that you call that specific function, instead of you have to copy the information from the memory of your host into the memory of your device. And be aware that most of the time that you are going to spend is to copy to and from between the two buffers. Okay, so you have to think about which kind of pipelines you want inside. So for example, if you have 3 layers, you want to make sure that you have a pipeline within the FPGA so that the information is passed from layer 1 to layer 2 and layer 2 to layer 3. Now, how do we define a kernel? So here's an example of a kernel where you have your input and you also then have your input. You are going to use pragmas. Normally we use pragmas before for loops. You have to check if the code that you have inside of your for loop is parallelizable or not. And if it's parallelizable, then you can do a pragma enroll. Now, you can also be specific. You can say how many loops or how many circuits you want to infer using the pragma enroll. Nevertheless, be aware of a fact. So when you start adding numbers, you may be spending 6 to 10 hours to get the tool chain to be able to compile, and there at the end you come to the conclusion that the device had no enough resources. So it requires a little bit of time here trying to understand. Another good aspect is if you are using OpenCL based acceleration, it's not fully compatible, but it's partially compatible, for example, with Intel devices. So I use both Intel and AMD/Xilinx FPGA boards. So instead of trying to go with these tools high level of synthesis, because they are too specific, if you go with OpenCL, you are speeding up the implementation process. Challenges: we have long compilation times for bitstream generation. Data transfer will be your bottleneck. Most of the time, the delays will come from copying the information from the device buffer into the from the host buffer into the device buffer, and vice versa. It is also may increase the optimization complexity, okay, but this is a decision, and my comment here is you have to decide what is best for you. So if you are a company and you want to commercialize, you may want to go in the VHDL and Verilog route. If you are an academic or you are doing research, you want to go OpenCL because you can even convert some of the code into, for example, CUDA, and run the acceleration on a GPU. So in terms of optimization, you have to think about loop unrolling, the memory coalescing, so aligns the memory access to the partner for efficiency, and kernel pipelining. So if you have 3 layers, for example, you need to think about how all of that is going to work. So that's where we are at the moment. I have previous publications, for example, implementing retinal models, and therefore that's why where we developed this knowledge and understanding, and we are about to publish about the implementation on the FPGA. In fact, I have the compiler running as we speak at the moment, compiling to run on the FPGA. What happens next? Well, there is an opportunity here for encryption, and anyone interested in looking into more into how to use these techniques to take the sound into the image and even vice versa, by all means get in touch. Okay. You start having encryption from the moment that you don't have a one-to-one correlation. So you could inject noise as represented here in this neural network. We already have an implementation in software. Once we finish the migration of the codec, we'll start doing also the compilation to use these techniques to start doing encryption. We are also expanding the number of metrics that we are using. The spike metrics are very important to let us know when to stop training. So we use Vitor Purpura and Von Rossum. We come to the conclusion that, for example, Von Rossum gives more or less the same results of Vitor Purpura in terms of distance, and therefore we are now exploring a little bit of other approaches. With some initial work, show that the final encryption errors remain below 1.2%, and they are very resilient to cryptanalysis tools. We are also in parallel running cryptanalysis tools to see if the information can be obtained using cryptanalysis approaches. So spike metrics is definitely something that we need to look into, because we need to know when to stop training. We can use this approach, for example, to encrypt security keys as well. Bio-inspired compute could be adopted more widely. So, for example, we are now talking about quantum AI, quantum technologies, and so on, but there is something in between, and FPGAs provide the right vehicle for us to explore, for example, encryption, because of what's happening. Okay, So I've covered that. This is our ongoing collaboration. So we have collaborations with National Institute of Technology, CoDec, Indian Institute of Technology from Bhubaneswar, and also Ulster University. We have the support from both Altera and AMD Xilinx, and also Sundance. And if you are interested to explore more, please get in touch. This is the contact of the teams, and I'm happy to take any questions that you may have.
Thank you very much. Any questions? Any questions online?
You also have the YouTube channel here in case you want to see some videos where we use these types of technology. You just need to scan with your mobile phone.
Okay, thanks everybody. It's now time for break for lunch, and hopefully see you after lunch break. Thank you, Dr. Mikado.
Thank you. Thank you.
Thank you. Bye.
Bye-bye.